Welcome to this week's episode of Leaders on a Mission, where I'm joined by inspiring leaders driven by the impact of creating a healthy and sustainable world. Now, in today's episode, I'm joined by Pavle Jeremić, CEO and founder of Aether Bio. Now, Aether Bio are a Synbio company using nanoscale machinery that can assemble new classes of molecules from organic and metallic atoms. And Pavle, we've been in contact for the last few years. You know, as I said to you, I saw your recent announcement and really wanted to reach out and have you come on the podcast and share some of your experiences and journeys. So thanks so much for giving me your time. I know you're a busy guy, so thanks for that.
Yeah, thanks for having me. I'm excited for this conversation.
Great. So, Pavle, just interesting, like taking it, I suppose, back a few years, what were the main kind of influences, that really kind of helped shape, where you are now, as it were?
So, I think, I think there's a couple things. I think if we go back quite a long ways, my childhood was quite unusual. I grew up partially in the United States. My parents were doing their PhDs, and so I grew up in their laboratories, or I was growing up in former Yugoslavia, whatever country it was that month or that year. And so, I think one of the most influential things in my entire life has always been, having my early childhood exist in two worlds, where in one world in the United States, everything was fine. University towns are pretty nice, even if you don't have a lot of money. And then the other world was, an active war zone. And I would come back to new bombed out buildings and playgrounds with craters in them. And so I think that was by far the most influential thing that ever happened to me, because it left a deep-rooted obsession with understanding why does this kind of discrepancy, this dichotomy exist in the world, and how do I fix it? How do I create a world where this discrepancy doesn't exist anymore on the better side? So I think that was one major influence. And then I think the other thing was, something that I've always been hugely thankful for was I was very fortunate in middle school and then mostly in high school. A professor at UC Davis, where I was growing up in my later childhood, just took me in and let me do my own synthetic biology research. And so, from my early childhood, I'd become convinced that I needed to change the world in a way that this sort of desperation, this sort of extremism was not possible anymore. I became convinced through reading books that had to be some kind of nanotechnology to build this future of abundance, but I couldn't figure out how to build it, right? Science fiction is fun, but I want to make it real. I don't want to write it. And then by working in a lab doing actual synthetic biology, I was very fortunate to realize two things. One, I realized that the closest starting point to real nanotechnology that I'd ever found was what nature had evolved over the course of billions of years. And to be clear, that is not the long-term nanotechnological solution. It is the starting point. So a lot of limitations to what nature evolved, because nature didn't evolve it for humans. It evolved it for its own purposes. But it's the closest thing I have, right? And believe me, if I had an easier starting point, I'd start with that, but that's all I have. So that was super exciting. And then I think the other major point of influence there was this realization that the human species has not really cracked the problem of engineering these nanoscale machines. And so through undergrad and through Aether, it was trying to figure out, how do we build a system where we can really quickly and robustly build protein-based nanomachinery? And once we get very good at that, we can then start to build even more complex machinery. So, I think those are some of the biggest influences in my life. It's definitely why I've been able to get to where I am today. Entering undergrad with several years of lab experience certainly helps.
Tell me a little bit about nanotechnology. What is it? First of all.
Yeah, let's talk about it. So let's first talk about what the objective of the technology is on a purely technical, not a commercial level. And then we can talk about how the technology does what it does. So on a purely technical level, I sort of hinted at earlier, but what we are trying to do is we are trying to figure out if we want to, for example, create an entirely new molecule. Now, that molecule could be a molecular hinge. It could be a building block for a next generation ballistic material. It could be a mechanism, like a mousetrap to capture lithium and pull it out of solution. If we want to build a nanoscale molecule, how do we build it in a very, very quick way? And how do we build it even if we've never seen any molecule like it before? Because one of the really, you know, I would argue significant differences about Aether, and it's something that I didn't really appreciate until recently, how significant differences was. We did not found Aether with the goal of biology building everything for the human race. We founded the Aether with the goal of using biology to create machinery that would eventually make biology obsolete. And what that means, what's kind of implicit in that plan, which I've recently begun to appreciate, is we cannot be limited by what nature has already invented, right? We have to build a technology where if I want to create a 60 carbon hinge, for example, that I can't make a bet that nature has already evolved something that makes a similar enough molecule that I can use directed evolution on. It's not an acceptable risk for us to take if we're to achieve our goals. So the technical objective of our platform, of our technology, is how do you, if you specify a desired arrangement of atoms, and you have all the different molecules that you can start from, all the different super cheap building blocks that are available everywhere, how do you design, using robotics to run the experiments, then machine learning to train from them, how do you design a nanoscale catalyst? You could call it an enzyme, you could call it a peptide. They don't look like proteins in nature very much anymore. So, you know, we're sort of out of luck in terms of easy terminology, but call it what you will. How do you design an amino acid based machine that's going to take these starting molecules that are super available and rearrange all the atoms and all the make and break bonds to get to the molecule that you want, and do so quickly, and do so even if you've never seen anything like it before. So that's the technical objective. But okay, how the hell do we do that? Because, you know, that's, as I've discovered the hard way, a very difficult problem to solve. But we have solved it now quite a few times. But when I was trying to figure out how to solve this problem, and it was clear to me we had to solve this problem from the beginning, because again, you know, the goal of Aether, if we're successful 10 years from now, maybe we're still working with some amino acid based or peptide backbone based machines, but we are working on even more complex machines than that are made from much more robust building blocks that we made using these initial catalysts. So when I was starting the company and trying to figure out how to do this, it was clear to me that humans do not have an intuition for engineering at the nanoscale, right? And I want to be clear about this. It's not, people talk about biology being why it's so hard to engineer. I don't really think that's true. It's not that biology is hard to engineer. It's that these protein-based nanomachines, they operate at the nanoscale, and everything that operates at the nanoscale is extremely non-intuitive for human beings. So it was clear to me from the beginning. So it could be non-biological, and it could still be extremely difficult to understand. I mean, there's condensed matter physics is also very, very difficult to understand, and it's at the nanoscale. So it was clear that we had to use algorithms like machine learning, or whatever the current nom du jour is. But as I was looking into this problem, it's a machine learning problem, I really framed it as, well, you have a protein-based design, and that's your data point. And if for any machine learning to work, you need labels of what does that machine do, right? What molecules does it make or break or bind to or whatever. And even when I was working at UC Davis in high school, you know, I was reading a huge amount of literature. I got in trouble for printing a lot of papers on the lab printer. And the PI was like, who just spent $600 on ink? And I was like, okay, that's my bad. I didn't appreciate how expensive printer ink was. But anyhow, I was reading all these papers, and I was finding these papers where people would say, well, there's this enzyme in nature that's known to do X, but we tested against Y, and it's totally different, does this totally different thing. And I kept seeing this pop up. And this is a more commonly accepted notion now, but the idea that one enzyme, one reaction is just totally bogus. And because of that, as I'm thinking about this problem of my protein and my labels, I realized that if we tested every protein against only one or two or three, or only a small number of different functions, we won't completely label what this protein can do. And if I want to design a machine learning algorithm that can very robustly design a new protein for a new reaction, I have to have good labels for my data set. So what I realized was, if we were going to do this, if we were going to build a platform to do this, a technology to do this, we would have to build a platform that could not only test an enormous number of different protein designs, but it would have to be able to test them against really diverse and wide panels of different chemicals, of different metals, do so in parallel. And it would have to be something that would be fast, because you're obviously increasing the number of samples you're processing by an enormous amount. It would have to be something that was about as what I would call untargeted as possible, because if I want to test an enzyme against 96 or 384 or 1536 compounds, if I have to develop a new assay for every one of those compounds, I'm just totally host, right? This is never going to work. And not only that, I can't, if I have to develop an assay for every potential product or every potential chemical reaction I'm going to see, I'm also host, because I can't predict in advance what unexpected chemical reactions are going to occur. Actually, now we can to some extent, but in the beginning, I couldn't bet on that. And the final thing was it had to be miniaturizable, right? Because running experiments in 30 microliters is fine if you're running only thousands of experiments a week. But if you're eventually running millions of experiments, that's not acceptable. That's it's going to hurt you on your ability to reduce cost. And as I was looking at all the different technical approaches that might work, what I discovered was there was one technical approach out there called laser-based mass spectrometry. And it's basically, instead of LCMS or GCMS or whatever your favorite mass spectrometry approach is, instead of using a needle to push through a filter and then push into a mass spec, you basically arrange your samples on a chip, you hit it with a laser ionizes the sample, and it flies into a time of flight mass spec. I mean, you can fly into whatever mass spec you want, but one of our machines is a time of flight mass spec. And I realized that this was fast, this is miniaturizable, and this was about as untargeted as it could be. We've been able to validate single assays ionizing tens of thousands of different compounds before. But I was kind of shocked. I'm always very suspicious when I find something that seems too good to be true, because I'm looking at this technique, which is a very niche mass spec technique. It's very rarely used. I'm like, why isn't everyone using this? Well, this just seems like a no-brainer. So I fly around the U.S. and I talk to a bunch of industry and academic labs, national research laboratories, sort of smaller university academic labs, all that kind of stuff. And everyone keeps telling me that the reason why no one uses this technique is because it's too noisy. And another way you can easily get me suspicious is if you claim something without having sort of a reasonably good first principles explanation of why that's true. And if everyone keeps saying it's too noisy, and I have friends that are running LiDAR companies that have to use a beam of infrared to recognize a toddler or a trash can on the road, I'm deeply skeptical that that is a harder problem or an easier problem than what we're doing in a laboratory controlled setting. And it turns out, I won't talk to too much of the details as we filed some of these patents and we're filing more, but it turns out that's not a real problem. There are surface chemistries you can use if you really start to understand how this mass spectrometry technique works, which I think we might be some of the most knowledgeable people on the planet now on how this mass spec technique works. You can really dramatically reduce the variability in the noise. And if you do that, you suddenly have a mass spec technique that can work on tens of thousands of compounds. It's thousands of times faster than anything else that exists. It's incredibly miniaturizable. We've actually run some of our experiments in 150 nanoliter samples directly on chip, which once we deploy that at scale, which we're not doing this year, but we'll probably do next year, our cost per sample is already lower than anyone else, but our cost per sample once we deploy that is going to be measured in less than a tenth of a cent.
Amazing, incredible. But most people, it's funny, but most people, go on and they research and PhDs, et cetera.
Yep.
But, it sounds like you're always going to be an entrepreneur at heart, really, right?
Yeah, I think, I was, both of my parents are professors. So I grew up in university towns. I was always surrounded by academia. And, I always wanted to have, if I'm going to create the future that I want to create, I have to be in a role that's going to be as impactful as quickly as possible. And so, I'm not sure that I knew I wanted to be an entrepreneur when I was a young kid because I didn't really know what an entrepreneur was, but it was clear to me that academia wasn't the route. It was not possible to have that sort of impact. And I think I came to the conclusion that entrepreneurship was the right way to do this because even though long-term, I think the long-term solution to this problem of scarcity in the human race has a political angle to it, I don't think the political solution is possible until you've made it technologically possible for 10 billion plus human beings to live and consume at the rate you and I do without destroying the planet and do so easily, right? Because the fundamental problem we have and that we will face over the next 100 years is that, we have been very fortunate to live in the part of the world, the few 100 million people that can consume at an enormous rate. And we are now very rapidly going to find, and we are finding that billions of other people expect, and I would argue deserve, to be able to consume at that same level of rate. And there's a lot of things that are getting better. Energy is one of the amazing things. I think the triumph of solar and the rapidly reducing cost of solar energy means that that's probably going to solve at least the energy generation part of our species problem. But I think that you have a more fundamental problem, which is industrial scale up is in the way it's been traditionally done using traditional synthetic chemistry or even traditional biology is incredibly difficult. It's slow, it's painful, it's capex intensive. I mean, a good example of this is it's just totally unacceptable that HIV is still a problem in sub-Saharan Africa. And it's a problem, I would argue, in part because it is so difficult to scale up the molecules that could treat HIV and eliminate it from our population. There's so much capex involved, they're so expensive to make that there is no financial incentive for these companies to build a $500 million facility in the Congo or in Mali or something like that. But if you could build a technology where it would be possible to be as productive as this $500 million plant, but your plant only costs $5 or $10 million, you've completely changed how the underlying dynamics work. You make it possible to very rapidly industrialize in a decentralized way huge parts of our planet in a way that doesn't destroy the environment, but also very importantly allows for the hundreds of millions and billions of human beings who deserve to live lives like ours to be able to do so and get to that point extremely quickly. So that's really what we're trying to achieve at Aether is that sort of a new technological basis for manufacturing that allows for, in a decentralized manner, extremely rapid scale up of industrial manufacturing.
At a cost-competitive price.
Yes, exactly. And I think that's really crucial. I think, especially when, I could pontificate about this for ages, but, as a company, we have to be sure at every step of our process that we're doing two things. That one, especially at this early stage, the first is that we are producing products that have a significant value proposition compared to anything else in the industry. It's very helpful that our technology is able to discover new chemistries that aren't feasible using either traditional synthetic chemistry or biology. That means that we can develop products that we're the only way to make that product work, right? So that's kind of a huge advantage we have. But it also means that we have to be very careful about the products we work on. I mean, I can tell you that there are chemistries we've discovered that could be really exciting from, for example, a green perspective. We have a new class of chemistry that it could probably revolutionize carbon capture from coal plants and flue gas, but we're not commercializing it right now because there's no path to commercialization over the next 2.5 years. And so as a company, we have to be incredibly disciplined, especially at this early stage, about build products that have value that people will pay for today, build products that are uniquely differentiated, and build products that can be built from the cheapest starting building blocks that you can find anywhere on the planet. I do think that, especially in the United States, I see a lot of synthetic biology companies, become enamored with, bio-based feedstocks. And the United States is sort of wildly unique in that we so heavily subsidize corn that, in the United States, sometimes corn is a reasonable feedstock, but that's not true in Kenya. That's not true in India. That's not true in most parts of the world, in China. So it's building a future of abundance requires constantly keeping an eye on, are people going to pay for this today? And is it going to be the cheapest possible way to make this? And if it's not, we don't do it.
Tell me, I suppose the challenge when you've got a platform technology like this, as you said, you can do, your mind must be going crazy with the things that you can do, right? And how you can apply it and the problems that you can solve. Tell me, how do you go about focusing on and finding the application and the real opportunity out there?
Yeah, that's a great question. So, I mean, you're exactly right. And I would actually say, when I talk to investors or talk to anyone really, I think one of the biggest risks for Aether is this, being stuck in a field of shiny objects and not being able to pick. And what I can tell you from my personal experience, because now we're not just a platform company anymore. We're actually making our products. We have a chemistry lab, quite a large chemistry lab. We're actually scaling up some of our products right now. I can tell you personally that I can focus on maybe 2 products at a time through scale up, and that's it. So focus is absolutely critical. But let's talk about how we do that. So we have a few stages, and we're quite strict on the stage gates that we have, and we're strict and a little bit more bureaucratic than you might expect for a company or stage, precisely for this reason. Because I'm, if I accidentally put on a back burner a super valuable product, well, that's fine. It's based off of a chemistry that we know about, so that's okay. It's just delayed it by a few years. But I don't want to accidentally work on something that's not going to pan out. So let's kind of start from the beginning. I mentioned this before, but I think it's good to kind of be very explicit about it. Everything we do at Aether is based off of what we call novel chemistry. And all that means It doesn't mean that it's a Nobel Prize winning catalysis or anything like that. It just means that it is a chemical reaction or a chemical functionality that, to the best of our knowledge, to the best of our ability to figure out, is impractical, infeasible, or impossible using either traditional synthetic chemistry or traditional biochemistry. And we always start there. And if we find out that there's another way to make this class of molecule, we usually kill the program at that point, unless we discovered that new chemistry and we've patented it, in which case, that's also a novel chemistry, it just doesn't happen to use a protein. That's fine. That doesn't, I'm not a zealot about this. And the reason why we do that, the reason why we're so strict about that is if I'm making a product that is possible using traditional synthetic chemistry, but I'm using biology to make it, for example, the fundamental bet that I'm making is that I'm smarter than 10,000 chemists at DuPont. I'm not a fan of that bet, right? There are a lot of very smart people working at a lot of other companies that know about all these interesting chemistries. I would much prefer to be working on products that 10,000 chemists at DuPont have been dreaming about for 50 years, but have never figured out how to get to, never figured out how to make. That's the place where we want to play in, because one, it makes us highly differentiated in our product offering, but two, I think it addresses a fundamental risk, because I think a lot of people, you should never assume you're the smartest person in the room or the smartest company on the planet. I think that's just a bad assumption to make. There's probably a reason why that product hasn't been created that you're not aware of yet, and you will find out the hard way. So we start there. And the way we find these novel chemistries, there's two different ways we do it. One is we discover them serendipitously. So when we're doing our incredibly high throughput multiplex screening of many different compounds against many different proteins, and we call that indexing, by the way. So our indexes you could sort of think of as two-dimensional grids of many different protein designs and many different chemicals or metals being tested in parallel. We routinely discover new unexpected chemical reactions in that process, and we just put that in our database. And I'm willing to bet that 90-95% of those are useless, right? Certainly, these are all sort of random chemical reactions that come up, but a good percentage of them are probably useful. So sometimes what we do is we put our product teams, which are just very talented chemists, in front of our database, and they just scroll through and they say, wait, you can do that? That could be huge in this industry. People have been looking at that for years. So sometimes we just find it that way. And a good example of that, actually, what is the best example of that? Some of our PFAS work is probably a good example of that. The other way we can find stuff is, our product team say, hey, we would really love to bind to lithium because we think there's a huge market opportunity here. It's aligned with our mission. Machine learning, can you find us something that binds to lithium? That's where our platform kind of iterates. And then the way we kind of stage gate this is, we have our team in the earliest stages of our pipeline, always thinking of looking through databases, talking to potential customers, and just building a backlog of interesting new chemical reactions that if we could find this could be valuable. As we ramp up the platform's capabilities, we then have sort of 3 stages of mature product development. The earliest stage, what we call discovery. All this means is it is our platform turning the wheel to see, can we find this new chemistry at all? There's no product development, there's some customer conversations, and there's a stage gates of, is the chemistry unique? Is it valuable enough? And can we find it? And we think that we will probably be doing 5 of those at most in parallel in our Series A timeline. And this is sort of the lowest bandwidth consuming version of our product development. Then we have something called benchtop or development. So this is where it really starts to ramp up in bandwidth and intensity. This is where we have proteins that do something interesting, and we are improving them, optimizing them, refining them, and we're actually building an end-to-end product. So for example, with lithium, we have, as far as we can tell, the first high affinity, high selectivity lithium binding proteins on the planet. It's really incredible the work the machine learning team and the platform team has done. But it's not good enough just to have something interesting, on a robotic system, say it binds to lithium. We have to actually be scaling up the production of those proteins. We have to be testing them in different filters. We have PVC pipes that are being joined together to create little simulacrums of what the full scale system is going to be like. So it's 2 sort of separate design loops. There's the platform design loop of make a better protein, and then there's the product design loop of, with the best protein you have, figure out how to make this work end to end. What are the right pumps? So are you getting calcium scaling? How do we fix that? All that kind of stuff. So it's really chemical and process engineering at that point, with just an input of a new protein every couple of weeks coming from the platform, a new better protein. And then the final stage is sort of the pilot stage, and that's really the final stage for us at Series A. And this is where we scale up a shipping container size system that shows on-site operation of our product, and it's sort of the de-risking to the point where we're able to then go out and either through equity or debt financing or through government funding raise tens of millions of dollars to actually go build a commercial size plant from that. And that's kind of how we, so, everything we do through this process, we're always checking, is it a uniquely valuable proposition? And the unique is important there. Is it something that customers won't shut up about? That's my signal when we're doing customer interviews. So something that I learned a long time ago through a program called ICOR, and it's sometimes called the Lean Launchpad methodology. And I don't remember all of it, but one thing that always stood out to me was you should never ever talk to in the early stages of customer discovery, you should never talk to your customers about what your technology is, because people get excited and that's going to confound your results. What you should do is talk to your customers about what their problems are. And if the problems that they won't shut up about overlap with the problems what your technology can do, there's a really good chance they're going to buy it. If they don't, they're not going to buy it. And so for me, when I'm flying around the world talking to these customers around the United States, really what I'm looking for is, will they not shut up about this? And to me, that's the indicator of, I'm saying I'm willing to spend a lot of money every month developing this into a real product, because I believe that someone's going to buy this at the end. And then the kind of final concept for us strategically, which I also think is important, is whenever you find a novel chemistry, there's a lot of things you can do with a new type of chemical reaction, right? There's a ton of products you could make. So how do you prioritize them? And something that I think is super important for us is this idea of stratifying products of tomorrow versus products of today. So a product of tomorrow is something that's going to take, the main thing that distinguishes them, there's a few things, but the main thing is a product of today is something that I think there's a reasonable chance we can commercialize in under 2 years, that I can sign a contract, I can do the product development, I can get it in customers' hands, and I get a contract signed. Anything that's more than that is a product of tomorrow. And usually products of today are not going to be multi-billion-dollar products. Now there's exceptions to that. Lithium is a good exception to that, but that's going to be a multi-billion-dollar product. But we don't set that bar. The bar we set for a product of today is, it is a beachhead market. It helps us understand how to do scale up, how to go to market in this market segment. And we expect it to generate tens of millions of dollars of revenue for us per product, but we don't expect it to get to maybe hundreds or millions or billions of dollars of revenue. But it sort of lays the groundwork for the product of tomorrow in the same space. So a good example is, we have these, in our materials programs, we've developed this entirely new class of additive, and I can't speak too much as to what the actual molecule is, but it's super interesting. And basically what these additives are is that they are designed by us, it's an entirely new class of molecule, so that when you blend them into high performance materials, when they're in one physical form, sort of chemical state, they change the properties of the material to make it more malleable, more processable, more 3D printable or extrudable, or whatever your preferred manufacturing method is. And then in a different chemical state, we can trigger the change of this molecule based off inputs like heat, or there's a few other things we can do. It strengthens the molecule on the back and it solidifies it. And so you have a high performance material that is easier to manufacture on one end, but then through the manufacturing process, it transforms the material into something that's much stronger on the back end. And what's cool about that is, trying to commercialize an entirely new material on your own, there's no way that's happening in under 2 years. It's just convincing someone to use a new polymer is a multi-year process. So most of our next generation polymers are products of tomorrow, which is 20% of our time at most. 80% of our time are on these products of today. And a good example of that is additive, because I'm not convincing our customers to use a new material. I'm just convincing them to blend in this powder that I can charge a lot for. They don't have to blend a lot of it in, and it makes their existing processes much more effective, and it gives them a better product on the back end. And so that to me is, for example, the first product we're working on, I expect it to end up in the tens of millions of revenue for Aether. It's not going to be a multi-billion-dollar product. It might end up at, close to 100 million a year in revenue within the next 5 to 6 years. But that's fine, because I'm learning how to do scale up for these classes of molecules, and that's laying the groundwork for the next generation ballistic materials that we're working on that will take 3, 4, 5 years to actually take to market.
That's great. No, thank you for the insights with that. Tell me, the product that you speak about, which you can bring to market, is the lithium product, right?
Yeah, so we have 2 products right now that are in that sort of benchtop phase. There's the lithium product, which is moving really well, and then there's that additive product for the materials, both of which are actually ahead of schedule, which is somewhat surprising. It's harder to bring stuff to market than I'd like, but that's fine.
Just when I read that, it just seemed like, you always think about Synbio and some of the challenges with climate and the really solving some of these big kind of challenges out there, and it's so well documented, the demand for lithium and the challenges when it comes to the mining of it. It just, like when I read it, I'm not saying it seemed obvious, but there was such a problem there to kind of solve. Can you just outline, what the machine does, what the process does?
Absolutely. So I think this is a really good example. I think the lithium problem is obvious. And it's obvious in part, if we just think about this geologically, lithium in nature tends to, over geological times, form a salt, right? It's an alkali metal, forms lithium chloride or lithium bromide or whatever its preferred pairing is. And so the problem you have with lithium when you want to extract it is, actually the first problem is there's something called the cosmological lithium problem, which is that if you look at the abundance of metals, they get less abundant as they get heavier, and they're sort of like a more or less aligned a little bit. But weirdly, lithium and beryllium shoot down and then shoot back up. And we don't actually understand why. So lithium is actually not that common. It's reasonably common. There's enough for the human race, but strangely, for reasons no one understands, it defies the pattern of all the other metals. And that's, there's a few potential reasons for that. But so the problem you have is that because lithium over geological timelines tends to leach out of rock as a salt, it tends to dilute itself, right? Whenever there's water, it will leach into the ocean, and the ocean has the most lithium, but the lowest concentration. We're not trying to extract from the ocean, right? That's just, even though in theory our technology could work on the seawater, the fundamental problem you have is that the lower your concentration of the metal you want to extract, like if 10 times lower concentration, 10 times more volume of water you have to pump, right? And energy costs become a problem at some point, and they're definitely a problem at seawater concentration. But the problem you run into with lithium is that there's very few places in the world where lithium is extremely high concentration. So for example, Chile, Bolivia, Argentina, these are the salt flats. And there the lithium concentration is high enough that it's actually commercially viable to do extraction today. And that's where any direct lithium extraction that's been successful so far is done there, because it's like 4,000 parts per million or more. It's crazy amounts of lithium in those brines. Then you have a handful of kind of oddities that are 500 to 700 parts per million. So that's like Salton Sea. There's some stuff in Utah. But the vast majority of the lithium in the world is less than 500 parts per million, and there's a lot in the US that's in the 100 to 250 parts per million range. And the problem that you run into when you're trying to extract there, if we just talk about the chemical methods, because no one has even remotely been successful using biological methods, but we'll talk about how we think will be successful. The chemical method for direct lithium extraction today is to take your brine, your water source that has lithium in it, let's say from the Salton Sea, which also is geothermal, so it's quite hot. And you basically run your brine over a filter. Usually it's some modified alumina sorbent, but there's several different technologies. And your filter is selective to lithium. And your filter might be 10 times more selective to lithium than any other metal, which sounds great until you realize that lithium is 500 parts per million in your brine, calcium is like 30,000 parts per million, sodium is 50,000 parts per million. So the problem is, even if you're only 10 to 1 selective to lithium, if calcium is like 100 times more abundant or more than your lithium, you're actually mostly extracting calcium or mostly extracting sodium or whatever, there's a few other metals. So a lot of these other technologies, the problem that they have is that they're not sufficiently selective to lithium. And so the two things become a problem there. Three things. The first is they have to pre-process a lot of metals out. And this is hyperbole. It's not strictly true, but I think it's a useful bit of hyperbole. It's almost like they have to extract every metal but lithium, and then they can extract lithium. And that problem gets worse. The second problem is that problem gets worse the lower your lithium concentration gets. Because if your lithium goes from 500 to 100 parts per million, it's not like calcium is lower concentration, right? That's still high. So your gap has increased. So you have to pre-process more, which is why everyone is trying to do direct lithium extraction at the Salton Sea, because people are not even certain that they can be commercially viable at that concentration range, even though most of the lithium in the US is that 100, 250 parts per million range, at least as far as we can tell. And the final problem you have is, even in the best case scenario, if you try and get everything out and you try to get lithium out, the companies that are the most successful today, they still only output, their kind of output stream is still only 50% lithium, 50% magnesium-ish, plus or minus a little bit. And the problem is battery grade lithium is 99.5% lithium, and there can't be any magnesium in it. So you basically then have to take your output and you have to send it to be refined. And most of the refining capacity in the world, I want to say somewhere between 60 to 80%, the numbers, I see different numbers in that range, are in China, which has its own set of geopolitical problems, and also just cost problems of adding, So, okay, so that's the problems with the existing approaches, and that's why people can't tap what seems to be by far the largest deposits of lithium in the United States in any reasonable level. Other people in biology, when you look at other companies trying to do lithium extraction, they're mostly trying to improve, and this is true with almost all biomining. The problem with all biomining techniques to date is they're basically trying to use some kind of acidophilic bacteria to replace acid leaching in mining. And there's two problems with that approach. The first is that acid leaching is possibly one of the cheapest processes you can imagine. Hydrochloric acid is one of the cheapest molecules on the planet. It's almost impossible to think of a cheaper molecule. I actually can't think of one that's cheaper. So you're already in a position where the only value you bring is that it's greener, and a well-maintained acid leachate pond is actually not that environmentally damaging. So the problem is if it leaks, but most of them in the US don't leak. They tend to leak in the third world where there's no kind of, there's no checks on did you actually build your dam well or anything like that. So that's not what we're doing. Instead, when we're looking at this problem, we realize, well, wait a second. If we could build a peptide-based machine that could be extremely selective to one metal and could also be extremely stable, right? So it didn't have to be replaced often. It could survive really high acidity. It could be reused thousands of times over and over again. And if it could be highly selective to one metal over all other metals, could we build a new process where rather than having this alumina filter that's somewhat selective to lithium, you have a protein-based filter that is hyper selective to just lithium. If we could do that, you get rid of your pre-processing, you get rid of that cost. You can access lower concentration brines. And what we're modeling right now for our pilot plant, we think there's a good chance that we'll be able to go directly to battery-grade lithium. So you get rid of the refining step. So not only does that mean you could domestically in the US produce battery-grade lithium, you also are wildly cost competitive. I mean, again, we haven't actually built the scale up. We've just done the level 5 DEAs, and we're validating some of the stuff in the benchtop scale. But I mean, we're looking at being in a position where at these lower concentration brines that are just completely inaccessible to anyone else, we are already going to be cheaper than anyone else on the planet in terms of lithium extraction. As we continue to improve the technology, we will improve that by somewhere between 2 to 5x on top of that, which just puts us in an incredibly strong position. And the reason why we're pursuing this as an Aether product, not licensing it out, is because it's incredibly aligned with our long-term mission of building a future of abundance. But also, the coolest thing about this is that these little proteins, they don't just bind to lithium. If I want to engineer a similar technique, a similar technology to bind to vanadium or titanium or whatever your preferred metal is, that's theoretically possible. And so what we're really trying to build are these semi-modular, it's never going to be perfectly modular, but semi-modular shipping container size facilities that you kind of hook up together almost like Tinker Toys that just take a dilute stream of some metal that's available somewhere in the United States, somewhere on the planet, and they just strip out that metal and they return the dilute stream just with that metal gone and no other contaminants in the process. Lithium is kind of our pilot project there for all the obvious reasons. It's also probably one of the hardest ones to tackle because lithium is so light. So there's reasons why from a process chemistry perspective that makes it challenging. But if it works on lithium, it'll 100% work on rare earth elements like samarium, erbium, but also vanadium. Titanium is an interesting one that could be quite exciting. If we can make titanium as cheap as steel eventually, that's something that's going to be world changing in its own right.
Amazing. So you would build, your scale up involves building a plant, a facility to build this particular enzyme peptide.
Right.
Right.
And to be clear, something that's important. I didn't really mention this in the beginning, but a strong point of view I have, which I insist on in all of our products, is to keep the biology as simple as humanly possible. And what I mean by that is, I don't care if there's an interesting plant-based enzyme that does some interesting chemistry. I don't care about that because even if I update the platform so that we can express plant-based enzymes and all that kind of stuff and all the post-translational modifications that are involved, I'm never going to be able to scale it up, right? I only want to work on peptide folds that are highly scalable. And I want to do that, one, because something that's so critical, and I mean, I can't emphasize this enough. Something we've actually learned the hard way, and that's critical to what we do now is, and a capability that we've built internally. Let's say that, our product team says machine learning, engineer a peptide that, binds to lithium. Say that's the target. And let's say they iterate on Monday, they submit their designs, by Friday, we have our data. of the first few thousand designs that were tested. And we have something that binds a little bit to lithium. I don't care that the robots tell me it binds to lithium. I want to immediately make 500 milligrams of that peptide and test it at the benchtop. That's when I get excited, because the thing that's fundamentally true is screening at the nanoscale is different than the large scale processing. And if you can't very quickly go from interesting hit to benchtop validation and characterization, you're screwed. Because it's just so easy to have confounding factors that you can't possibly predict all of them. So inevitably what's going to happen, and what we see happen is, some of our hits that go from kind of the robotic scale to the benchtop, some of them disappear, some of them behave totally differently. That's just inevitable. We can't, you can never perfectly simulate the larger scale environment. So for us, what's critical, by keeping the biology simple, we put ourselves in a position where, one, we can very quickly check and scale up our protein to a point where we can actually characterize it. That's one. But two, when you look at the commercial scale up, not just kind of this laboratory characterization scale up, it means that we can quickly generate kilograms or even metric tons of our proteins. There's a lot of different ways to scale these guys up. And the reason why I'm okay, I've had people tell me before, well, the plant enzymes do unique chemistries. Aren't you giving up on those chemistries? I actually argue that's not true. So there are examples of chemistries we are giving up on. A good example would be nitrogen fixation. The only way nature does that today, for the most part, is using this very complex cofactor called FOMOCO that has molybdenum and cobalt and iron. It's just nuts. It's a very complex process, and it's a very complex set of enzymes. That's a good example where the complexity of the protein is actually aligned with the new chemistry. But a lot of the time, like terpenoid synthetases are a good example of this. A lot of the time, the complexity of the protein, all the post-translational modifications that make it hard to scale and produce, they actually don't have anything to do with the chemistry. They're orthogonal, and they just exist because in this plant cell, this enzyme needs to exist in a certain part of the cell. That's not relevant to us. We don't care about that. So I would actually argue that over time, we should be able to recapitulate most of the complex so-called eukaryotic chemistries in incredibly simple, totally novel folds that are incredibly stable as well through some chemical modifications we do. And then over time, as we sort of start to include non-natural amino acids and all that kind of stuff, we should start to expand the boundaries of chemistries even beyond anything that nature ever intended. So yeah, that was so we basically, sorry, that was a very long-winded way to say we can actually work with CMOs to scale up our proteins, and that's something we do sometimes. That's actually not a problem. Yeah. For us, the scale up is more about actually the end-to-end product. So for the peptides that bind to lithium, for example, I want to have a shipping container deployed by the end of next year that you hook up a pipe on one side that has water that's lithium coming in, and you hook a pipe on the other side that takes water out that doesn't have lithium in it. And we have a drum that's just filling with battery-grade lithium.
Well, yeah, no, that's great. Thank you. And well, tell me, with your Series A, I just wanted to touch upon that. It's been very challenging kind of marketplace over the last kind of year or so. So
yeah,
just tell us a little bit about the journey and the experience. Particularly what the real learnings were for you, and any advice you can kind of offer entrepreneurs.
Yeah. I mean, I would say that you should expect your fundraise to take dramatically longer than you wanted to. I mean, to the point where I'll tell you that we really had to cut burn during our fundraising process. In fact, I actually had to furlough the team at one point. We were just at the finish line. I came up in front of the team. I said, guys, we're about to get there, but we need to furlough everyone, and myself included. And I think it was somewhere between 2 and 4 weeks. And fortunately, the team stayed together, and I was very proud of them for that. But those are the kind of decisions you might have to make, because so let's talk about the fundraising market, at least my experience. And what I'll say is, this is my experience. I don't want to pretend that I'm the best at fundraising. I'm not, if you've founded successfully companies before, your experience will be easier. That's just a point that I want to make clear. But also then you have your own experience. So take everything I say with a grain of salt. But there's a couple things I've noticed. One is just in synthetic biology in general, the market is incredibly skittish about synthetic biology plays. And it's for reasons that make sense. I mean, honestly, I was saying for years that a lot of the synthetic biology companies fundamentally didn't make sense. That I didn't understand how they were going to commercialize. And unfortunately, they raised eventually billions of dollars and IPO'd with almost no revenue. And this is just a recipe for disaster. So we are, I think, seeing something of a winter in that space. And I think it's really being driven by the fact that investors are, if you're not generating revenue, it's going to be hard to raise money. And that's not true for super early stage, right? There's still an opportunity to raise substantial money at the early stages. But I think really that transition from seed to Series A, it used to be, I won't name names, but there were companies that raised crazy amounts of money that no longer exist, that raised their Series A off an LOI, not even revenue, right? So that's not possible anymore. You can't get anywhere near that. So that's one thing. And so I think having a plan that, if you're going to go out and fundraise, a plan that works, even if that fundraising takes a year, to actually pull the money together. And that means making hard choices now. I think the other thing that I learned, which was really fascinating, was, so in the before times, before the sort of everyone freaked out, people, if you secured your lead in a priced round, in my experience, it was then very easy to get follow-on. That is not true anymore. And again, in my experience. So in my experience, if you secure a lead, at least for Series A, for a company as CapEx as intensive as we are and as difficult as ours is, the follow-on did just as much diligence as the lead. And that's what I kind of said at the beginning. I actually think that's probably good overall for the market, because I will say that there are companies that have VCs that have invested in us that did zero diligence, and I was happy to take their money, but at the same time, I was like, do you even understand what you're investing in? And what I'll say is, that's actually a piece of advice I do have. I think that obviously accept money from who you can, right? To build, beggars can't be choosers, especially in this market. But what I will say is, if a VC is doing very thoughtful diligence on you, in my experience, those are the best VCs to partner with in the long term, because they understand all the thorns that exist and all the ugly parts and how hard this is going to be. And they still say, I want to do this. This has to exist. And in fact, like the guy who led around, Jay Zaveri, I remember that one of the things that absolutely sold me in partnering with him was, we were at a dinner at one point somewhere in Menlo Park. And at the end of the dinner, he said, I'm paraphrasing, but he said, Pavle, this company is going to be harder to build than you or I think today, but it needs to be built. And just that kind of mentality, I think just makes the best partners to work with in the long term. So that, I think expecting that if you secure a lead, it's probably going to take a while to fill out the rest of the round. At least it was in our experience. And I think just being focused on the go-to-market. How are you going to develop product? How are you actually going to get customer feedback? How are you going to start generating revenue? I think these are things that companies should naturally do, but I think that the almost decade of free money led to sort of a lack of discipline in the Synbio space. And I really think we're paying the price for that, where, companies were able to raise billions of dollars with with actually zero product market fit. I'm sure something similar will happen in generative AI. I think there's huge potential in that, right? Obviously. But there's a lot of companies raising a lot of money. And so this is sort of, whenever there's a bubble like that, just be careful. I think, and also, we saw this even because that sort of brief mania, and I think it was 2021, 2020, something like that, where companies raising a ton of money again, and then a lot of people IPO'd, and then they sort of crashed. A lot of those companies, it's coming back to bite them, right? I think it's very dangerous in a mania to raise tons of money. And that's actually, there's a lot of things. I have a lot of thoughts on this. I think the last thing I'll say before I'll shut up is, I do think it's really important to think to yourself, what's actually the right amount of money to raise? I think when I started Aether and when I started as an entrepreneur, I always heard people say, be careful not to raise too much. Or if you raise a lot, make sure it buys a lot of runway so you can hit more milestones. And, I understood that theoretically, but I didn't really understand it. I think now I really understand what that means. Raising a lot of money puts a lot of expectations on what you have to achieve. And I think you have to be really careful about that, right? I think building a company, especially with something like Aether, is a long-term play. We're not going to IPO next year, right? And so I think you really have to keep in mind for how much money do you really need? How much, then put some buffer on top of that. And then if you have an opportunity to raise more than that, think carefully to yourself, what does that buy you beyond what you're originally going to do? Because if it does buy you something really valuable, awesome, then it could make total sense, and put a little buffer on that and then run with it. But if you don't think there's anything else that buys you, the dilution and the expectations that it comes with might not make sense. And that's, it's for everyone to decide, but yeah.
What are the dreams and hopes for Aether over the next kind of 10 years?
So, I think the first obviously we have to bring our first products to market, but really from a mission perspective, I think the thing we have to figure out over the next 5 years is really two distinct things. The first is we have to figure out how to generally solve the problem I brought up at the beginning of define an output arrangement of atoms and be able to build a machine that can make that happen. And do so in a sufficiently robust and broad way that Aether as a company 5 years from now is just prototyping new molecules, and it's sort of a foregone conclusion that we're going to make the molecule, we're going to test it and see what it does. The second thing we have to figure out is really how to build, and I call them the dreadnoughts, but really how to actually build modular shipping containers out of factories. If we can figure out, we build our first prototypes for mining or for material synthesis, and we really get really damn good at rearranging atoms in a robust way. The second phase of the company, which starts a little less than 5 years from now and then continues on for another decade, is really scaling up these dreadnoughts. So Aether as a company is a company that is going to really try to achieve two things over the next 15 to 20 years. It's first going to try to achieve the massive acceleration of abundance in every single industry we can find, both from taking existing molecules and making them much cheaper, which is not something we do today because it's harder to do, but we will in the future. That's one angle, but also the other angle is driving the availability of molecules that couldn't even exist today, but making them cheaply available anywhere on the planet, whether that's pharmaceuticals or that's entirely new classes of nanomachines or polymers or whatever that is. If we can get to the point where, suddenly we can build an entire materials industry in the Congo, or we can take WHO essential medicines and manufacture them everywhere on the planet at incredibly low cost, take the most impacted essential medicines and say, back of here for HIV, we are just going to build hundreds of these shipping container sized factories and just set them up across the world so that, you just have a pill press after that. And we have now hopefully achieved a level of elimination of the HIV plague. Being able to achieve these huge impacts in the human race, it really requires to be good at those two things. How do we scale up the dreadnoughts as quickly as possible, which is a really challenging chemical engineering, mechanical engineering, and process engineering problem, right? It's certainly not going to be easy to do that. And eventually we'll have a huge factory that builds these dreadnoughts, and just sort of the inputs are proteins, molecules, and steel, and the outputs are shipping container sized factories. And then the other problem is, how do we really get good at designing those catalysts in the first place? I'm actually being kicked out. I think I grabbed the wrong room. But Simon, it was great to talk to you.
It was wonderful talking to you. Listen, I really appreciate you coming on. All the very best, and we'll catch up soon.